Okay, I think the recording has begun. So yeah, chapter 6, energy, work and power. Like I said just now, actually back in Sec 1, you have learned the foundation of this, like you said, without the formula. So let's begin. I start off by showing this video actually. If you want, you can go and catch up on this video. This video shows this guy who actually used a blender. He put water in a blender and blend it all the way until the water start to boil. So in that case, it's like a bit of like electrical energy converted into kinetic energy where the blender spins, and the spinning, the kinetic energy became thermal energy and causes the water to boil. So he managed to do it like of course not by hand stirring, but really just with the help of a blender, like yeah, stirring long enough. So yeah. So we start off talking about energy. So back in Sec 1, you have learned that energy can be transformed from one form to another, and yeah. So in this first part, you will learn about what is energy, the different forms of energy, which is nothing new. Yeah, so energy is the capacity to do work. The SI unit of energy is joules with capital J. Energy is a scalar quantity. It has only magnitude. There's no direction when it comes to energy. So these are the common forms of energy you're expected to know. So for potential energy, there's 3 types: elastic potential energy, gravitational potential energy, and chemical potential energy. Okay, so later we'll go into each one of them, what each one of them are. And then there's also kinetic energy. These two are also known as mechanical energy, but we rarely use this term. We use more of these two, potential and kinetic, but you see these two the most. Yeah. Then there's electrical energy, your thermal energy, or heat. Heat is actually thermal energy when it's being transferred from one body to another. We call it heat. On its own, you say that it's called thermal energy. Then there's your light energy, nuclear energy, there's also like sound energy and so on. So there's many different forms of energy. How do questions actually ask and check your understanding on the forms of energy is they'll probably give you a scenario. And like, for example, just now, the one that I showed you about the guy using a blender and stir the water until it boils and all this. So they'll ask you, like, for example, can you state or can you describe, the energy changes in the system? So how did the energy transform gets converted from one form to another? So in that case, just now was electrical energy to kinetic energy to thermal energy, kind of stuff. So that's usually how it's being tested. So you should know how to identify the different forms of energy. So we start off with kinetic energy. Kinetic energy got to do with movement. So any object that's moving will have some form of kinetic energy, and this kinetic energy can later be used to do work. So for example, when wind in windy places, it moves the turbines, and these turbines, this kinetic energy can later be transformed into electrical energy. Next year in Sec 4, in one of your last topics, electromagnetic induction, you will learn how this kinetic energy can be transformed into electrical energy. Then, for example, a ram can be used to break down the walls. So the kinetic energy, when it hits into the walls, when the wall breaks, no work is being done. Next, we have potential energy. The 3 types of potential energy, just now we said, is actually energy that's stored in a system. So your chemical potential energy includes, for example, a battery. When a battery is not being in use, it's just on its own, we call it a chemical potential energy, because there's actually energy in the battery, but it's just not being used yet. So when it's being used, this chemical potential energy gets converted into electrical energy. Then, for example, for your trees, it itself was also chemical potential energy. When you burn it, this energy gets converted into light, and converted into thermal energy, and so on. Your food that you eat is also a form of chemical potential energy. After you eat the food, your body digests, it converts this chemical potential energy into like kinetic energy where you can move. It converts into like thermal energy to keep you warm and kind of stuff. Okay, then elastic potential energy, just from the name elastic, you should know when you stretch elastic objects, it stores elastic potential energy, which when it's being relaxed, that's where the energy is used to do certain work. Like for example, in this case, you stretch the rubber band will store elastic potential energy. You stretch the bow, it stores elastic potential energy. When you let go, this elastic potential energy gets converted to kinetic energy when the arrow flies out. Yeah. And of course, gravitational potential energy, you learned that back in Sec 1 also. Basically, it got to do with the height of the object. Something that is higher will have more gravitational potential energy. Yeah. Okay, so then in terms of workbook, okay, this question I went through already. So principle of conservation of energy, basically this was something that I've already heard back in Sec 1. It basically states that energy cannot be created nor destroyed, but it can only be converted from one form to another, and the total energy in an isolated system is constant. So this is a very important concept when it comes to physics. It guides us in a lot of calculations and so on. So time to time, there's a lot of people who try to come up with those machines that can go on forever, that can, energy can be created out of nowhere, those perpetual machines, but none of them will ever work simply just because of this principle. As long as you remember this principle, you know that those perpetual machines will never work. They will usually, they have to gain energy from somewhere, or they'll lose energy somewhere. Eventually, they will stop moving on its own. Okay, so yeah. So these are some examples when it comes to principle of conservation of energy. This is important because it guides us in our calculations. Okay, so I think you will notice when we are going through the workbook that quite a lot of questions actually relies on this principle of conservation of energy to allow us to know how much is our energy and so on. Later I'll be going through quite a handful of examples, step by step, with more difficult examples along the way to illustrate to you how we can make use of this principle to help us in our calculation. So for example, over here in this example, there's this guy who is cycling. So when he's cycling, there's a kinetic energy. So this energy, because there's a bicycle dynamo that's connected to it, he's able to harvest some of this kinetic energy into electrical energy. And this electrical energy is later converted into light energy because as the light bulb of the dynamo, but of course, it will not be 100%. Some of this energy is actually lost as maybe friction, thermal energy. There will also be some sound, so they will lose some energy here and there. But in the end, the total amount will still be 20 joules. Okay, it's very important to recognize that overall it will still be the same. That's the principle of conservation of energy. So after that, the class did a question to check their understanding. But basically over here, a nail is hammered into a plank. What energy does a raised hammer possess? So because it is raised, it's higher, it possesses a gravitational potential energy. Then when it falls, what energy is this energy? So it becomes kinetic energy because as it falls, it is moving. And then after that, it is used to drive the nail into the plank. So that's what the subsequent energy is being used for. And what are the other energy forms produced? So when we hit, there will be some kind of sound, there will be some friction or heat. So there will be sound energy or thermal energy and so on. Yeah. Okay. So another very important example that is usually discussed, okay, when it comes to this topic is pendulum. I would guess that in Sec 1, actually, this example was mentioned, but yeah, now it's brought back again, and you'll be doing some kind of calculations with it also. So we start off by saying that when the pendulum is displaced to, let's say, W, it actually has some it gains some gravitational potential energy relative to the original position. So when the raised pendulum is released from W, it swings back to the equilibrium position of Y, where it's supposed to be at rest. So when it swings, this GPE that it possesses over here is converted into kinetic energy. So when the GPE is at Y, the GPE is minimum, while the KE is maximum. One thing you notice is they say that the GPE is at its minimum, and they did not say the GPE is 0. Okay, because I did mention in class that GPE is a relative concept, in the sense that there isn't really a zero GPE, because even when this at its lowest point, let's say I cut the string, this pendulum bob will still fall. So there's still GPE, but based on the setup of this system, when the string is tied to it, at point Y, it is at its lowest. So we consider that as the zero, or like the minimum GPE, to be more accurate, instead of saying that it's zero. But for KE, we can say 0 KE. Okay, if let's say the object is not moving. Okay. So for an ideal pendulum, when we say ideal, we assume that there's no air resistance and there's no loss in energy. So from Y, when it swings upwards to Z, the new position, it loses the KE and it gains the GPE. And because it's an ideal pendulum, all the energy, all the KE over here will all be converted to GPE, and it's able to achieve back the exact same height. Okay, because it's an ideal pendulum. Okay, so it's the same height as being released because of conservation of energy. So when it swings over to this side, it will just reach over here. There's no energy loss, okay, to overcome air resistance and friction or whatsoever. No. So summary, in an ideal pendulum, you can see that from W to Y, the initial GPE here will be equals to the final KE over here. And then from Y to Z, the initial KE over here will be equals to the final GPE over here. So there's no energy lost along the way. But of course, in real world, okay, there is always energy loss due to like friction or drag, air resistance. So some of the energy will always be lost to the surrounding into, like, let's say, thermal energy, sound energy, and whatsoever. So this thermal energy, lost to the surrounding and cannot be converted back into kinetic or gravitational potential energy. So it's lost. It can't be converted back into useful energy. But the total energy is still conserved, meaning if you account for this energy loss, the total energy in the system would still be the same. What do we mean? So let's take a look. So in the same story, if we account for, let's say, energy loss, let's say in the case of a non-ideal pendulum, where there's air resistance, what happens is when W goes to Y, the initial GPE over here will be slightly larger than the final KE here. So you will see that in terms of writing out in equation, the initial GPE here will be equals to the final KE here plus any energy lost due to air resistance. So over from here to here, there's already energy lost. Then from here to Z, this will be even lower than X because there's not enough energy to bring it all the way to the same height. Okay, so the initial KE here will be equals to the final GPE here. Of course, there will also be some energy lost. So throughout the whole process, there'll be energy lost, and you will just keep getting lower and lower and lower until it eventually comes to a stop. Okay, so far, can follow?
Yeah, so it means the non-ideal, it will never go back to the original position.
Correct, because energy is lost along the way.
Okay, yeah.
So when you look at questions, you just need to read the question. If the question says that, like for example, in a story it says, let's say the surface is smooth, so you'll know that, oh, there's no friction. If they so you look out for certain wordings, or if they say that there's assume no air resistance, then you can assume there will be ideal, there's no loss in energy. So if they never say much, there could be energy loss. So you just do the calculations and see how the maths work out. So later I'll be going through some examples to help you better see that. Okay. So I think that day in class, I brought the Newton's cradle for everyone to just play around and just take a look. So in that case, you notice that when you take up the bulb and you let it swing down, GPE is converted to KE, KE strikes, and then over here, the K is being transferred over, and then it's converted to GPE, get raised up, and so on. But along the way, because it produces sound as it hits each other, there's some heat loss and all this, and over time, the energy is quickly lost to the surroundings, and it will just come to a stop eventually. Yeah. Of course, because the design of the pendulum, of the Newton's cradle, the one that I bought was actually a pretty cheap one. I think just a few dollars kind of thing. So yeah, it's not very efficient. A lot of energy is lost to the surrounding, and it's quickly, yeah, it could quickly like stop. Those more efficient one, they can go on for a longer period of time. So principle of conservation of energy. So this is another example, similar to the pendulum one. Just now we said the pendulum in a non-ideal scenario, you'll not be able to swing back to the exact same initial height. So same thing for when a ball bounces. So let's say this is the original height the ball drops from. The GPE is converted to KE. So the GPE decreases, K increases. Just before reaching the ground, K is maximum and GPE is at its minimum. So on contact, energy is lost, to the surrounding due to heat and sound. The total amount of mechanical energy is now lesser. Okay, so when it bounces up, while this K is converted to GPE, because there's a lesser total energy now, while this GPE increase and K decrease, it will not return to the original height. Okay, so at the maximum height, KE is 0. Like I said, we can say that KE is 0 when the object is not moving, but we do not say that GPE is 0. We only say GPE is minimum. So if you dig the ground further, you can still go further. So yeah, but then when an object is not moving, you can say that KE is 0. So at this point, GPE is at its maximum, but however, due to energy loss during the bounce, the height of the ball reach will be lower than before. Okay, so just one final example before we move on to another new concept in the case. So let's say over here, we have a softball player throws the ball into the air, catches it on the way down, state the energy conversions that take place. So same thing over here at the lowest point, when you first threw it, the speed will be the highest. So as the maximum KE and minimum GPE, as it goes up, okay, this KE is converted to GPE, so it slows down all the way until to the top. KE is 0, okay? So at this moment, for a split second, it's not moving as it changes direction, and it starts to fall back down. This is where the GPE starts to get lost again, and it regains back as KE, and then come all the way back until here, where the GPE is minimum and the K is back to the maximum. Okay, so yeah, these are the practice questions which I have went through. Later at the end, we can go to visit some of these questions if you're not sure of some of the things that I went through and you would like to, ask. So this is a new concept which I think I did mention that day when we go through the workbook. By the principle of conservation of energy, the total energy output by a machine must be equal to the energy input. But of course, we say that in real life, the useful energy output is always less because some of this energy is lost or dissipated due to friction or as a form of sound and thermal energy to the surroundings. So this energy loss is considered wasted energy output. So not all the energy input becomes useful output. So you can imagine in terms of the input, the total energy will be equals to the useful output plus wasted output. Okay, but this is the one that we want. This is the one that we try to minimize. So when it comes to calculating efficiency, we are looking at how much of the total energy input is actually useful energy output. Does that make sense to you? I repeat again, when we're looking at efficiency, we are looking at the percentage of the total energy input that becomes useful energy output. If I'm more useful energy output, that means that it's more efficient. If I have less useful energy output, this means that it's less efficient because more energy is wasted. Okay? So you look at this, so energy input can be converted into useful one for doing work and wasted one such as heat and sound. So in terms of calculation, the formula looks like this. Efficiency equals to the useful energy output, which is what we want, divided by the total energy input times 100%. I think pretty straightforward, pretty simple. Yeah. How can I apply this calculation? Engine of a toy car is capable of producing 1,000 joules of energy. A boy lets the car run on a rough floor. So when you see rough floor, it means that there's energy loss, there's friction. 400 joules of heat is generated due to friction. So this is the energy loss due to friction. So determine the efficiency of the car. So we take efficiency is useful output over energy input times 100%. So the useful output will be 1000 minus the 400 that's wasted as friction. So 1000 minus 400 divided by the total input, which is 1000. So this gives us 60% efficiency. You understand?
Yeah. Okay.
Okay, this one I get a class to try. Another similar example. A worker pushes a heavy box up a rough ramp. The GPE gained by the box is 2000 joules, but the amount of work done is 4000 joules. So useful work is 2000, input is 4000. So what is the efficiency? So the output 2000 over 4000 times 100%, this gives 50%. So where did all the excess energy go? So when he pushes it up, some of the energy is become, like thermal energy. He do for exercise, some of this input becomes like heat and all this. There can be friction and all this. So yeah. Okay, so with that we cover the front part about the different forms of energy, how energy is converted from one form to another, and the principle of conservation of energy guides us that the total energy is always conserved. There's no loss. It's only converted from one form to another, and we also talk about efficiency, which is there's some form of calculation to it, where we look at how much of the energy input is actually becomes useful energy output. So we just take useful energy output divided by energy input times 100%. So far, okay? Is it too fast?
It's okay. Can understand.
Sorry?
It's okay. Can understand.
Okay. Do you need me to slow down, or this pace is okay, or?
Yeah, I think it's okay.
It's okay. Okay. So you need me to slow down, just let me know, because it's just one-to-one. Okay. So we move on to work, something that you have learned in Sec 1 also. So we also start to learn the formulas on how to do some calculations. So after that, in terms of recall, we watch another video. You know what? Must as well let me show you the video lah. And just now that one also. So okay, this was the one that I showed just now. Maybe I just show you also. Are you able to hear?
I think no. I
Can you hear?
can't.
Okay. Okay, I'll skip this part. Basically, it will take quite a while until it becomes boiling. You can see over here the temperature rising. It's just blending, and it reaches like 98, 99 degrees Celsius. Okay, not sure where the sound went to. But yeah. Okay, so basically this is what this video is about. Then we move on to the other video. This is the pendulum. Okay, so I think there's a very simple demo to illustrate that. Yeah, GPE. Okay, so you give it a little bit of push, or you'll go more than where it started off. If not, you will never be able to go higher than it. That's why the guy over there, he was quite confident, like he can just put his head there. As long as you let go, as long as there's no push, the bowling ball will never hit his face. Yeah. Okay, so we go back to bring about one of the first few formulas you learn back in Sec 1 about work. So what is work? Work done. How do we define work done in physics? So work done by a constant force on an object is calculated as the product, of the force and the distance moved by the object in the direction of the force. Okay, so W equals to F times S, where S is the distance, or we also represent as displacement, moved in the direction of force. Key thing is the distance once you move in the direction of force. In the previous chapter, we learned something similar, force times distance, but for that, the distance was the perpendicular distance between the pivot and the line of action of the force. So that one is a different calculation, even though both are force times distance. For that, the moment is defined, it has a units of Newton meters. But over here for work done, when you have force times distance, work done has a units of joules. Okay, so yeah, so in the case is different. So yeah, an SI unit of work is in terms of joules. 1 joule is defined as the work done by a force of 1 Newton, which moves an object through a distance of 1 meter in the direction of the force. Okay, so some example, if you push a stroller with a certain force and it moves by a certain distance, the work done will just be the force they applied multiplied by the distance that is being moved forward. However, no work is done when the direction of the applied force and the direction in which the object moves are perpendicular to each other. So like for example, in this case, you are applying an upward force on the books so that it does not fall off, but you are moving it to the right. So in that sense, there's no work done by this upward force lifting the book because it's perpendicular to the direction of motion. Another way to look at it is basically the force applied on the object does not even move at all. So like for example, you push onto the tree remains stationary, technically no work is being done. Same thing if you're just standing there holding on to a pile of books and the books did not move, then in that case, there's also no work done because there's no distance moved in the direction of the force. So example where there is, for example, a boy pushes a box across a rough horizontal floor. He exerts 5 newtons to move it 2 meters. What is the work done by the boy? So 5 newtons, 2 meters. So force times distance moved, 5 newtons times 2 meters, you get 10 joules. So far, okay?
Yes.
Okay. So another example, slightly more complicated to merge together with a little bit of content from chapter 3. So a boy pulls a 1 kg toy wagon along a smooth horizontal floor. So smooth means that there's no friction over a distance of 5 meters. What is the speed of the wagon increases at a constant rate of 2 meters per second square. So means the acceleration is 2 meters per second square. So speed increases at this rate. Remember, acceleration is the rate of change in speed. So it's meter per second square. That's the units. What is the work done by the boy? So you need a formula for resultant force. So in this case, first they make use of that formula. F goes to m times a, where m is 1 kg. Acceleration is 2 meters per second square. So 1 times 2, so 2 newtons. So the resultant force is 2 newtons. And because is a smooth horizontal floor, the resultant force will also be the pulling force because there's no friction. So you can assuming that the pulling force is 2 newtons over 5 meters, there will be 10 joules of work being done. So far, okay?
Why do we need to actually calculate the net force?
Oh, because over here, to find the work done, you need the force multiplied by the distance. So you need to know what is the force. So in this case, to find the force, you make use of F goes to ma because you know the mass, you know the acceleration, you can find what is the force. And why is the, like I say, why is the net force same as the boy's pulling force? Is because there's a smooth horizontal floor, so there's no friction. So the only force acting on the toy is just the pulling force. So we know that the net force, which is the resultant force, is just the same as the pulling force.
Oh, okay.
Okay, so that's why you can just sub 2 newtons here. Okay, can I? Okay. Okay, so the next part, we are going to bring in the formulas for kinetic energy and gravitational potential energy. That's one of the main new things that you will learn from this topic. We start with kinetic energy. So when a force moves an object, it does work on the object and the object gains kinetic energy using this formula where kinetic energy is half mv square. Mass must be in kilograms. Velocity or the speed must be in meter per second. So it's given to you in other units. You need to do some conversion. So meaning the object gives you in terms of grams. You need to convert it in. You need to convert it into kilograms. Okay, before you substitute in to do the calculations. So some example. You have a 50-gram toy car moving at constant speed of 2 meters per second. Determine its kinetic energy. So kinetic energy is half mv square. M is 0.05 kilograms. And then the speed is 2 meters per second. So take note, remember to square it. So you take half times 0.05 times 2 meters per second square. So it becomes 0.1 joules. So key thing to learn from here, pay attention to the units, convert into the correct unit before solving the problem. Next, we have gravitational potential energy. So gravitational potential energy is the energy due to its position above the ground. To find the GP of an object near the surface, we need to consider the work done to lift the object to a height h above the ground at constant speed. This trying to show you a little how this calculation of GPE is related to calculation of work done, where we take work done as the force multiplied by the distance traveled in the direction of force. So we assume that the gain in GPE, meaning how much GPE it gains when you lift something up, work done, or we sometimes you will see the question will tell you as work done against gravity. So basically, it's just the force to lift it up. So we calculate it by we assume that this is equals to the weight, because that's the minimum amount of force you need to lift it up. So as long as your upward force is at least equals to the weight, you can lift the object up. So lift the object up, this F, which is the weight, just multiply by the height of increase. So since the object is lifted at constant speed, the F will just be equals to mg. Then since work done is force times distance traveled in direction of the force, this F is just mg, so mgh. So this is the formula for gravitational potential energy. How do we do this calculation? Just a quick, simple example. We have a 5 kg block raised 50 meters from its original position. What is the gain in GPE? So we use mgh. M is the mass, which is 5 kg. G is the gravitational field strength. On Earth is 10 Newton per kg. And then h is the distance moved. So in this case, it's 50 meters. So we take 5 times 10 times 50, you get 2,500 joules. So yeah, this is the work done or the gain in the GPE. Okay, so yeah, so these are just very basic examples to get you to see calculations. Of course, during exam, you do expect more difficult examples, which for the next couple of slides to come, I'll just be introducing to you examples after examples, where each example will slightly get a little bit more complicated than the previous examples. But it's the main thing that I will be illustrating over the next couple of examples is how do we apply the principle of conservation of energy to assist us in our calculations. Of course, I will make use of the formulas from kinetic energy, half mv squared, GPE at mgh, and work done is force times distance. Okay, so let's begin first by just recapping some example. So let's say over here, if the ball is initially at this position, it has a GPE of, let's say, 500 joules, and it's initially at rest at 0 joules. So when it reaches the bottom, all the GPE of this 500 joules is converted to become KE of 500 joules. So along the way, this GPE just get converted into KE. So let's say drop by 2 meters, let's say 200 joules get converted to KE, drop by another meter, another 100 joules get converted to KE, and so on. So as it goes down, you notice that the total energy is still the same. So in this example, actually what they are highlighting is also where it's an ideal system, where principle of conservation of energy indicates that there's no heat loss. The total energy is still 500. So this is the first example where it gets slightly harder. So let's take a look together. We have a 500 grams ball dropped from a height of 10 meters. What is the initial GPE? So I think it's quite straightforward. GPE is just mgh. M, 500 grams is 0.5 kg. G is 10 Newton per kg. H is 10 meters. So for 0.5 times 10 times 10, you get 50 joules. So this is the initial GPE of the ball at 10 meters. So determine the velocity just before it hits the ground. So basically, it's just asking you to calculate what is the velocity, okay, at the end. So by principle of conservation of energy, the initial GPE will be all converted into its final KE. So the gain in the KE will be equals to the loss in the GPE, which is 50 joules, because all of these 50 joules will all be converted into KE. So we can say that this KE of half mv squared is equals to 50 joules times half. M is 0.5, then v squared. So you just key into a calculator, do some rearrangement. This one is kind of like algebra. So yeah, v squared is just 2 times 50 divided by 0.5. Okay, because this one get multiplied over this one, comes down, they do a calculation. Take note, this is v square. So the common mistake is people forget to square root after they do the v square. You need to square root this answer to get back your v.
For this one, do we need to do the plus minus square root?
For physics, usually no, because because energy is a scalar. There isn't a negative to energy, so we can just treat that here. Just okay. So our example is going to go slightly harder from here. So now still the same ball, 500 grams dropped from a height of 10 meters, but now they say there's energy loss due to air resistance at 10 joules. So they ask you to what is the velocity just before it hits the ground. So previously we calculated that the initial GPE is actually 50 joules. So now previously we know that all 50 joules of GPE converted into KE. So the KE is actually 50 joules. But here they tell you that no, actually 10 joules is lost due to air resistance. So in that case, you take 50. So this 50 of initial energy is equals to the final K plus energy loss of 10 joules. Then from here, you know that the final K is actually just 40 joules. Then you do the same calculations, you realize that the final velocity is actually 12.6, which is lower than what was calculated in the previous question, where there is no energy loss. Okay, just a quick one. I think that day in class, I did highlight a particular, can say there is a formula. So I say that, you can always see all the problems as initial KE plus initial GPE will be equals to final KE plus final GPE plus energy loss if there's any. Okay, so in this ball dropping example, so before it drops initially, it will not be moving. So the initial KE is 0. Then the initial GPE, you just follow mgh. The final KE will be the maximum at half mv square. Okay, the final moment, the GPE as lowest, we assume that is 0. And the energy loss is whatever there is to calculate. So in this case, it's just 10. You just do all your calculations, you'll be able to get, the answer. Okay, so the simpler examples will have some parts 0, so you don't need to calculate them. So we start to, move on to slightly more complicated examples. So this is the exact formula that I just wrote just now. Initial K plus initial PE will be equals to the final K plus final PE plus any energy loss. So still the same now, thrown vertically downwards. So because it's thrown vertically downwards and not dropped, there will be an initial kinetic energy. Okay, and then it bounced from a height of 10 meters with a velocity of 5 meters per second. Okay, so hits the ground and bounces, then it rises to a maximum height of 8 meters. Determine the energy loss at the bounce. So in this case, if you want to draw out the example, oops. Okay, so in this case, there's the initial push. Of 5 meters per second. So the initial KE, so we wrote down this, which is exactly what I just told you just now. Initial K plus initial GP will be equals to final K plus final GP plus any energy loss due to the bounce. So in this case, the final K will be 0 because when it bounces and reaches the highest point again, this higher point will always be KE 0 because at that split second it's like kind of floating over there, not moving anywhere. So this not moving, so the K will be 0. Then the final MGH, you may use of mg times 8, whereas the initial MGH, we have mg times 10 because, yeah. Then half mv square, you know that v is 5, you just substitute in. Okay, you can find that energy loss is about 16.25 joules. Okay, do you need some time to digest this question? Can follow?
Yeah.
Okay, yeah. Okay, we move on to another example. We have about 2 or 3 more examples. So you can see as the example progresses on, it gets slightly more complicated. We're also going to integrate some topics together. So in this case over here, a car exerts a constant engine force of 10 kilonewtons. It is able to accelerate constantly from rest at a speed of 30 meters per second in 10 seconds. So it means from not moving to 30 meters per second is only 10 seconds. So determine the work done by the car and its kinetic energy at the end of 10 seconds. So in terms of the final KE, you can take a look at you need to first know what is the final speed, because the K will be half mv square. Okay, you need to know what is this V. Okay, so they take the final speed of 30 divided by the time of 10 seconds to find that the acceleration is actually 3 meters per second square. Okay, so this is the acceleration. So you know that this is the force, you know the acceleration. Using F equals to ma, you can find the mass. Okay, so you know that 10 kilonewtons, which is 10,000 newtons, divided by 3 meters per second square, you get this is about the mass of the car. So they ask you determine the work done by the car and its KE at the end of 10 seconds. Okay, so maybe let me write down a little bit more in terms of the breakdown. Work done, you do. Okay, let me write down. Work done, you do force times distance. Kinetic energy, you do half mv square. Okay, so in terms of the force, you know the force. In terms of the speed, you know the speed. What you need to know is the mass and the distance traveled. So we can find the mass using F equals to ma. So we just did over here, 3,330 kilograms. How do we find the distance traveled? We can use this velocity time graph. We learned that in velocity time graph, the area under the graph is the distance traveled. So it's just half times 30 times 10. Okay, so in this case, it will be 150 meters. Okay, so of course, now that you know what is the distance traveled, you are ready to calculate both of them. So this one, half mv square, half times this mass times this square, you know what is the KE. For this one, you know there is 10 kilonewtons times this distance traveled. Okay, so 10 kilonewtons times the distance traveled 150 meters. This is the work done. KE half mv square, half times the mass times the velocity square. Okay, so this is the slightly more complicated question where it takes a few steps. Usually during exam, we try not to have so many steps, in the sense that if we want to, we break it down for you. Maybe ask you to first calculate the distance traveled, ask you to calculate the mass, It will ask you, so we bit by bit ask you to do the calculations so that you won't like, because you cannot do one, then the whole question like a lot of marks got. Okay. Another example, this example is slightly more difficult to understand because it got to do with more like a ratio kind of thing. So they tell you the speed of a springboard diver decreases by half on entering the water. By how much will his KE decrease by? Okay, so if speed decreased by half, will the KE also decrease by half? Okay, you know that speed is half mv squared. So if the speed decreased by half, actually the KE will decrease by 1/4. Okay, because it's a square of the half. Okay, so they ask you how much it decreased by. So it will actually decrease by 3/4. But how do we show the calculation? So this is how they show the calculation. They say that the second speed is actually twice the initial speed, because they say decrease, I mean half of the initial speed, because they say decrease by half. Okay, so if let's say the initial KE is half m vi square, so the initial speed, okay, so the final KE will be just half m vf square. But what is this vf? Vf is half of the initial speed, so we substitute in half m half vi square. You expand this bracket. Okay, oops. Yeah. You open up this bracket, you have half m 1/4 vi square. Okay, so how is this? How can I compare this to the initial kinetic energy? Because they say how much did it decrease by? You need to compare the final KE to the initial KE. So if I do some rearrangement, okay, so this one will just be more of equals to 1/4 half mvi square, and this half mvi square is the initial KE. So this is 1/4 of the initial KE. So basically it drops by 3/4. A little more complicated in the mathematics, but if you think about it logically, I think it's still okay. Can follow?
Yeah.
Okay, if not, just one last question for this. So you saw we go a lot of examples. I try to show a bit of variation also. Okay, so yeah. So last example over here, there's a 100 kg hammer lifted to 20 meters, then it drops. So this is how they hammer the piles into the ground. Okay, so let's say they tell you that this 100 kg hammer at 20 meters, when it drops down, it loses about 15,000 joules of energy due to friction and resistive force. Due to friction is 15,000 joules, resistive force about 4,000 joules. Determine the depth which can be driven to the soil. So first, you need to calculate what is the initial GPE. This initial GPE will be equals to the final KE plus the energy loss, because when it falls, this GPE will be converted into KE. But of course, some of it will be energy loss. So initial GPE will be equals to the final K of the hammer plus energy loss. In this case, we don't take into account any form of initial KE because it's dropped from rest. We also don't take into account of any final GPE. We assume that it has fallen 20 meters, so all the way to the ground. So MGH, initial GPE is 100 times 10 times 20 MGH. Then final K is what we are trying to find. The energy loss is 15,000 joules. So yeah, so this one is just this minus 15,000. So you take this minus 15,000, you get about 5,000 joules. So this K, the useful KE that you get out of this whole dropping is about 5,000 joules. So they assume that all the KE, this 5,000 joules, is used to push the pile into the ground. So this is the work done by the hammer. So the work done by the hammer is 5,000 joules. The resistive force is about 4,000 joules times the distance traveled. So you take this, you calculate that the distance that the pile will move is 1.25 meters. So assuming, so yeah, this assuming that all these are converted directly. So this 4,000 newtons is the resistive force because it's pushing against the resistive force of the ground to drive the pile in. So this is the force in it. So we're coming to at least have 4,000 newtons. Yeah. So far, okay. I think examples are the more heavy part to this. We start off with some simple examples showing you how to calculate KE, how to calculate GPE. Then we started to bring across, how we link using the conservation of energy and how we bring energy loss in our calculations. Then after that, there's some examples that show you, for example, how we bring in the other topics like F equals to MA, and also like how do you do by ratio and kind of stuff. So yeah, basically that is all the examples that was that we went through in class. So that was what you missed. After that is power lah. Power is actually that day I think I went through briefly in class. So maybe I just do a quick one. I think it'll be less than 5 minutes. So power, we know that energy is the capacity to do work. Work is the product of force and distance moving the direction of force. So what is power? So I mentioned in class, layman terms, people will say power, energy, work. They treat them like all the same thing, but in physics, each of them means slightly different stuff. So power is defined as the rate of work done or the rate of energy conversion. So rate, previously we have learned it a few times. Rate means per unit time. So work done per unit time or energy converted per unit time. So yeah, W over T or E over T. Okay. Key thing to know is the units. SI unit of power is watts. How do we calculate it? Energy per unit time. The energy must be in joules. The time must be in seconds. So actually 1 watt is 1 joule per second equivalent. Okay. So yeah, 1 watt is defined as the rate of work done of 1 joule per second. So just an example, an engine does 60,000 joules of work in 10 minutes. What is the power? So power is work done divided by time. We take 60,000 joules divided by 10 minutes times 60 seconds. So there will be 100 watts. So yeah. So this is another example. They tell you that this is the power. They ask you the maximum amount of thermal energy you can generate in 1 hour. So 1 hour is the time. So power is energy divided by time. You sub in the power as 1850 watts. You sub in the time, 1 hour converted to seconds will be 60 minutes times 60 seconds. So you multiply the energy will be 6.66 times 10 to the power of 6 joules. So this is why they call it the maximum amount of thermal energy, because this is assuming that all this power is converted into thermal energy. Of course, we know that it will not be so perfect. There will be energy loss in the system. So this is just the maximum. One thing is we are sure is it will never exceed that, but unlikely it will be equivalent to that. But if I want to do simple calculation, assuming no energy loss, we will take this as the amount of thermal energy it can generate. We also talk about the concept of horsepower, because in the past, before all these engines were discovered or invented, people uses horses and all this. So horsepower is 1 horsepower is about 746 watts. So they are trying to tell you that the Porsche having a larger horsepower is able to do more energy per unit time. Okay. So just a simple example. Last one before we end off the day. So they tell that the electric motor in a washing machine is 1 kilowatts. Efficiency is about 40%. Find the useful energy produced in half an hour. So what they do is first they calculate the this 1 kilowatts based on half an hour. That will be P equals W over T W equals to P times T. So P is 1000 watts. Then time, half an hour is 30 minutes times 60 seconds. So the amount of energy is 1.8 times 10 to the power of 6 joules. But then they want the useful based on a 40%. So I'll take 40% of this 1.8. This gives me about 7.2 times 10 to the power of 5 joules. Otherwise, yeah, there's the whole of the chapter. Do you have any questions?
I think no more. Yeah.
In terms of the workbook questions, do you have any